Let me take a problem where I have two charged spheres that are charged by the same amount and which end up repelling each other. They are hung from the ceiling by a silk thread of length L, and what you see here is that they make the same angle with the vertical known as theta because their masses are the same. If the masses were different, these angles theta would be different for each ball. How do you charge these spheres in the first place? Let's first assume that they are metallic. Metals have the property that their outermost electrons, known as valence electrons, are not very loyal to their atoms, and they are easily convinced to leave the atom. So I'm going to bring a charged rod nearby. This rod can be something like a glass rod. So if I rub a glass rod against silk, the glass rod obtains a positive charge. I'm just going to bring it near the metallic ball without actually touching it. Now, because unlike charges attract, the negative charges, the valence electrons, are going to be more drawn towards the right side of the sphere, leaving the positively charged ionized atoms on the left side. Now, if I remove this rod back to the right, the situation here will go back to normal. But that's not what I'm going to do. While this rod is still at this position, I'm going to attach what's called a grounding wire. The term ground refers to the earth, and the symbol for the ground is a series of horizontal dashes of decreasing width. What this grounding wire does is it allows electrons to flow from the earth. The earth is assumed to have an infinite supply of whatever charge you need. In this case, electrons are needed by the left side because the atoms there are hungry for an electron. They're going to go and neutralize this side. They won't go here because these electrons will repel them. Now what I'm going to do is I'm going to remove the ground wire. Then you have an excess of negative charge on this side. Then remove the rod. So these negative charges will redistribute themselves and make it a uniformly negatively charged sphere. I repeat the process, keeping the same distance with the other sphere, so they are both equally charged. So I have mass m and charge q on each sphere. This method of charging an object without losing any charge that you bring into the picture is called charging by induction. It only puts opposite charge on the object. You cannot put the same kind of charge. If you want to put a positive charge, you need to bring a negative rod. So let's try to solve this problem. What we are trying to solve for is you are trying to find the charge q that has been deposited by this induction process. And maybe we'll also find the number of electrons. And if we have time, let's also find out what percentage of the surface has been ionized. Okay, let's try these problems. The law that helps us solve this free body diagram is Coulomb's law. The electric force is given by kq1 q2 over r squared. In this case, q's are the same, so it's kq squared over r squared, where r is the distance between the two spheres. Assuming these are really small spheres, we can take this radius to be that between the centers of those two spheres, for example. By geometry, r equals 2 times L sine theta, because L sine theta is this distance and r is 2 times that. Next, we have to solve Newton's second law, or force balance. Newton's second law says the sum of all the forces in the x direction equals 0. We'll take our traditional x and y directions here. And let's draw some free body diagram forces. Here's the force of tension, the force of gravity down, and the electric force. Because it's a force of repulsion, it will act in this direction. This angle is also theta. So Ft In the x direction, ft sine theta, that's this distance, ft sine theta must equal fe. In the y direction, I have, for equilibrium, I'll have fg equals ft cosine theta. Let me call this equation 1 and that equation 2. What I wish to do is solve for the charge. I don't require tension, so I'll divide 1 by 2. So I get Fe over Fg is equal to tan theta. Let me substitute now for Fe and Fg. Fe is kq squared over r squared, and Fg is just mg because it's gravity, and that is equal to tan theta. Now I can solve for the charge q. While I do that, let me also put r equals 2l sine theta. So r squared will become 4 L squared times mg sine squared theta times tan theta divided by the Coulomb constant K and the square root of that whole thing. So this is our expression for the charge. By the way, there's no other way of finding the charge on an object than such means, indirect means. You don't have a meter that can measure charge. Let's do a numerical calculation of this to see what we are looking at here in terms of orders of magnitude. So let me try the following values. Let the mass of the metallic ball be 10 grams, which is 10 to the minus 2 kg. We'll take gravity to be 10 meters per second squared because this is just an order of magnitude calculation. I'm going to take theta equals 45 degrees, which means tan theta is 1 and sine theta is root 2 by 2, so sine squared theta is just half. The constant K is Coulomb's constant, which has a standard value of 9 times 10 to the 9 Newton meter squared per Coulomb squared. Those are the SI units. And we have to assign some value for the length. Let me take length equals 1 meter. So let me substitute all these values in. The 4 will come outside, so that will be 2 times mass G L squared sine squared theta tan theta divided by K kg meters per second squared is just the same as Newton. There's a meter squared that goes away, so I get Coulomb in the numerator. So that gives me 2 times the square root of, that's 10 to the minus 1. 10 to the 9 comes upstairs and becomes 10 to the minus 9. And here I have 9 times 2, which is 18. So that gives me 2 over 18 is 9 times 3. So that's going to be square root of 9, which is 3. 18 is 9 times 2. So that's what I get there. And that's 10 to the minus 5 when I take the square root. So that's what I have. And that's going to be 2 over root 2 is just root 2. Root 2 is 1.4 divided by 3 times 10 to the minus 5 coulombs, which I can write as 14 over 3 times 10 to the minus 6 coulombs. 10 to the minus 6 coulombs is also called a microcoulomb, and 14 over 3 is approximately 4. So I've answered our first question. The second question is the number of electrons. How much has the Earth lost in this process? The number of electrons is got by taking the charge, which is 4 times 10 to the minus 6 coulombs, and dividing it by the charge of a single electron. And that is 1.6 times 10 to the minus 19 coulombs. That's really tiny. So I'll get 4 over 1.6 times 10 to the minus 19 when it goes upstairs becomes 10 to the positive 19 minus 6, which is 10 to the 13. And there's no units. So this is actually coulomb per electron. So the units are going to be electrons. I can write this as 40 over 1.6 times 10 to the 12. Okay. And 40 over 1.6 is approximately 24. So that's 24 trillion electrons. And that's 24 trillion electrons per metal sphere. So the Earth is out 48 million electrons. It might seem like a lot, trillion electrons. It might seem like a lot, but the Earth has got really a lot to spare. Now the last question is the percentage of the surface of the sphere that's ionized. Now it's because these are metals, most of the surface phenomena are going to be most of the phenomena are going to be on the surface, not inside the sphere. Let's assume something about the sphere next. I'm going to take the sphere to be 1 centimeter in diameter, or in radius. Now, most atoms are not very different from hydrogen atom in size. So let me take the atoms to be hydrogen atoms, even though I've told you it's metal. The size of a metal atom is only marginally different than that of a hydrogen atom. So the hydrogen atom radius is 0.5 times 10 to the minus 10 meters. 10 to the minus 10 meters is sometimes called an angstrom, written like that. A with a 0 on top of it. So let's find the surface area first. The surface area of this sphere, I'll call it a ball, that's 4 pi times the radius of the ball squared. So that's 4 pi times radius of the ball is 10 to the minus 2 meters. So that's 10 to the minus 4 square meters. The atom surface area, the atom size area, the atom is only going to present a disc-shaped profile. So atom size area is going to be that of a circle, pi times the radius of the atom squared. The atom's radius is half times 10 to the minus 10. So when I square it, I'm going to get 1/4 times 10 to the minus 20 square meters. So the number of surface atoms that I have I'm just going to divide the radius of the ball by the radius of the atom's cross section. So that's the pi's will cancel out. So I'm going to get 4 times 10 to the minus 4 divided by 1/4 times 10 to the minus 20, which is 16 times 10 to the 24. Actually, hang on, not 24, 10 to the 16, because 20 minus 4 is 16. Not bad. 16 times 10 to the 16, and we need 24 trillion. So calling 24 the same as 20 and calling 16 the same as 20, we need 1 trillion, and we have 10 to the 16, which is let me see if I can get this right. It's 10,000 trillion. There are 10,000 trillion surface atoms, and we need 10,000 trillion. For every 10,000 trillion, we need 1 trillion. So it's just 1 in 10,000. So the percentage is really small. So we only need 1 in 10,000, which atoms are ionized on the surface. So you can see that there's a potential for a lot more charge.